on the rotating system.
Okay. Do you have it there?
Yep, just finding the velocity observed, the acceleration.
Okay.
Just getting a little bit confused.
Yeah. Okay, so rotating coordinate system. Number 3. Let's see. Okay, so you have this disc thing that rotates, and then you have a hinge on the edge of the disc and an arm that goes, this arm goes up and down as this thing rotates. The disc has a radius of 0.5 meters. And the arm has a radius of has a length of 0.3 meters. And the disk rotates with an angular velocity of 0.1 t. So it's rotating around like this at 0.1 t. And the arm goes up and down according to the function. So if this is theta, theta is, as a function of time, is equal to sine of t. Calculate the acceleration of the end of the arm. So sort of what you would think we would do if you call that point P. We want to calculate the acceleration of P. At a specific instant. So the acceleration of P when time is equal to 0.5 seconds. This coordinate system rotates with the disk. So X, Y, and then Z coming straight out. Okay. Well, the first question is, are we going to use a coordinate system where the origin is accelerating and or the axes are changing orientation? What about the origin? Is the origin of that accelerating? No. But it is rotating with the, if you think of the disc as the horse and the arm as the cowboy, it is rotating with the disc. So the coordinate system is rotating with the disc. And so we're going to use this expression, the acceleration of p is equal to the acceleration of p observed in the rotating coordinate system plus the angular acceleration of the coordinate system crossed with the position vector plus 2 times the angular velocity of the coordinate system crossed with the observed velocity of p plus angular velocity of the coordinate system crossed with angular velocity of the coordinate system cross p. Okay, well, we know that so the 0.1t is what tells us about the rotation of the coordinate system. Okay. The other one, the sine function, just tells us about the rotation of that arm. So what do we know? Omega, capital Omega, the angular velocity of the coordinate system is the way I have it drawn here, about the positive y-axis. And so it's 0.1t 0. Any questions about getting that out of the information shown? This is a function of time, and so we can just take the time derivative of those components to get capital Omega dot. That's going to be 0.10. And then we can evaluate this at the instant given. The only reason we needed the functions was to take that derivative. Well, let me wait on that. Let me write them as functions for now. So now we'll figure out what the motion looks like of the arm. Well, in that coordinate system, to an observer in this coordinate system, the disk moving is irrelevant. And the person in this coordinate system just sees this arm moving up and down. And so that's a rigid body motion, or a circular motion about this pin. Okay. So you can think of this as so the observed velocity of p is equal to lowercase omega crossed with the r vector. Lowercase omega is, well, if that theta is sine of t, omega is the time derivative of so what's this angular position? It's rotating about the positive z-axis. So this is going to be the time derivative of 0, 0 sine t. And that's 0, 0 cosine t. Everybody with me on that? And the r vector is so the r vector goes from the center of the circular motion, from the pin to the point that you care about. And so that is the length, 0.3, times cosine and sine of that theta. And that is in the, so it's going to be 0.3 times cosine of theta for the x component, 0.3 times sine of theta for the y component. But then we have a function for theta. And so this is equal to 0.3 times the cosine of the sine of t. And then 0.3 times the sine of the sine of t. And the acceleration of the point P that's observed in the coordinate system is the watermelon equation. So that's alpha crossed with r plus lowercase omega cross quantity omega cross r. So what do we know about alpha? Omega we know is equal to 0, 0 cosine t. So alpha is equal to the time derivative of omega. So time derivative of 0, 0 cosine t. And so that's 0, 0 negative sine t. We already know an expression for omega and an expression for r. And let's see. So now we also need, we have those. Okay, so, and then the position vector, what about the position vector? We need an expression for that. That's the last thing we need. Not the last thing we need in a bad way, like that's the final thing we need. Okay, so remember the r vector goes from the center of the circular motion to the point of interest. The p vector goes from the origin to the point of interest. So this is just, we want the vector that goes from here up to p. That's just going to be r with an additional 0.5 in the positive x direction. Okay, so the p vector is equal to the r vector, which is 0.3 cosine of sine t, plus 0.5, because this time we're going from the origin, not from the center of the circular motion. And then 0.3 sine of sine t, and then 0. By the way, there's two ways you could do this problem. So I used circular motion to calculate the velocity vector and acceleration vector that are observed in the coordinate system. But since here we have an expression for the position vector, you can also just take the time derivatives of the components. That's just the other definition of the observed velocity and observed acceleration. Okay, so now we want to find this at a specific instant. So now let's evaluate all of these at time equal 0.5. Okay, so here's what we're doing again. So first, omega was 0.1 t0, and omega dot was 0.10. To evaluate omega, we're plugging in time equals 0.5 seconds. So this is equal to 0.050, and omega dot is equal to 0.10. Next, the observed velocity vector is 0.3 cosine of the sine of 0.5. This has to be in radians. Anytime you're taking derivatives of trig functions, you need to be in radians. So can someone tell me what that is? 0.3 cosine of sine of 0.5. Sure, that would be great. Okay. And the omega vector, lowercase omega?
That is
0.876? 8776?
Yep.
Okay. And then if you multiply these two together, the velocity that's observed is 0.8776 crossed with 0.266, 0.1380. And what do you get for that?
negative 0.1211.
Okay.
And 0.2.
0.2334. I like the style where every calculation you just add.
Yeah.
That's good. That's how you tell the chemistry teachers you're not going to put up with their nonsense.
It doesn't end well.
Okay, so we got the observed velocity vector. Now we need the observed acceleration vector. And to do that, we need alpha. What's lowercase alpha? So the way we did it, that negative alpha, or that lowercase alpha, is just 0, 0, negative sign of 0.5. Okay, so 0, 0, negative 0.479. Okay, and from that, we'll say that the observed acceleration is 0, 0, negative 0.479 crossed with 0.266, 0.1380 plus 0, 0, 0.8776 crossed with what comes out to be negative 0.1211, positive 0.23340. And what do you get for that?
Nine.
0.139. Okay.
Negative 0.2.
Okay. And then 0. And now we can put this all together. So the acceleration of P is equal to the observed acceleration, so negative 0.139, negative 0.2340.
Were you able to unpause it?
I think I did. Yeah. And then plus 0.10 crossed with the position vector. Did we figure that out? Did I forget to do that one? 0.1380. Okay, plus 2 times capital omega, the angular velocity of the coordinate system, 0.050. Crossed with the position vector, crossed with the observed velocity vector. So negative 0.1211, positive 0.2334, 0, and then plus the angular velocity of the coordinate system, .0.050, cross quantity 0.050, crossed with the position vector, which is 0.776, 0.1380. Okay, negative 0.1409. 0.234. Okay. Negative 0.065 something. Okay. Meters per second squared. One thing that's worth noticing about this one is there are two ways to calculate the acceleration. You know, you can think about it two different ways. I mean, it's the same formula, but the acceleration of p is equal to the acceleration of p that's observed in the coordinate system plus capital omega dot crossed with the position plus 2 times capital omega crossed with the velocity of p that's observed in the coordinate system plus capital omega cross quantity capital omega cross p. Okay? But that's equivalent to the acceleration of p is equal to the second time derivatives of the components of the position vector plus omega dot cross p plus 2 times capital omega crossed with the first time derivatives of the components of the position vector plus capital omega cross quantity capital omega cross p. And so there's two ways to do this calculation. The way I did it was in this whole example, I thought about the motion of the arm that's observed in the coordinate system as being a circular motion, and I used the circular motion equations to find it. Okay, but we also could have just come up with the functional representation of the position, which we did somewhere. So where's the position? So right here, we calculated the position as a function of time. And so instead of doing circular motion to get the observed velocity and acceleration, we could have just taken the time derivatives of this, and we would have gotten the same thing. So you'd have to use the chain rule. It's a little bit of a messy derivative or whatever, but you have two ways to do it. And when you have two ways to do it, that also means a way to check your work, which, you know, probably like in a class, I mean, I know like I never spend a lot of time like trying to check my work, but when you're actually doing a project or something, ways to check your work are like more precious than gold. They don't come up that often, you know, and so when they do, it's a way to make sure that you didn't make any mistakes. Any questions about that problem? Okay. Any other homework questions? Page title. Page width. Okay, so the example I want to do, I guess might as well start it today. We have a hinge connected to a wall, and a bar coming out of the hinge, and then another bar connected to the first bar by another hinge. And so this one has a rotation this way if it's counterclockwise. The second bar has a rotation, I guess, let's choose a coordinate system. So if the coordinate system is X to the left, Y up, Z out of the page, then a positive X rotation about the second member would be like that. Let's think of this first one as 5 radians per second, and the second one as 10 radians per second. I'm not going to use any angular acceleration. It just keeps the equations more concise, but I'll talk about where those would go in. And then the lengths, let's make both of these lengths the same. So let's make this 0.2 meters and this 0.2 meters. And we want to calculate the acceleration of p at the instant shown. Okay, so the coordinate system, we have one of those problems where we have two bodies, and one of those bodies has an axis of rotation that depends on the position of the first one. So it's a horse and a cowboy thing. This one is the horse, this one is the cowboy. So the coordinate system has to be fixed to the member that's horizontal here. And I already drew where we're going to put the coordinate system in this case. So is the origin of that coordinate system accelerating? No, it's just doing, as that thing moves around, it's just doing this, but the origin is staying in place. So we don't have to worry about relative motion. Next time I'm going to do this same problem, and I'm going to put, the coordinate system is still going to move with the horse because it has to, but I'm going to put it out here, okay? And then in that case, the origin of the coordinate system is moving in circular motion, and so we're going to have to take into account the fact that the origin's accelerating, okay? But right now it's not. So the acceleration of the point P is equal to the acceleration of P that's observed in the coordinate system plus omega dot crossed with the position vector plus 2 times omega crossed with the velocity of P that's observed in the coordinate system plus omega cross quantity omega cross P. This one, so in the last example, I pointed out after we were done that there were a couple of ways to calculate the observed acceleration and the observed velocity. In this one, there's not. So why in this one isn't it helpful to think of that as the time derivatives of the components of the position vector? There's what? Yes, exactly. We don't know so we will know the position vector at this instant, but we don't have the position vector written as a function of time. If you have it written as a function of time, you can take your derivatives. If you don't, you have to think of it in terms of circular motion or whatever kind of motion you have. Okay, so first, capital omega and capital omega dot. So which of these is relevant for capital omega? The 10 radians per second or the 5 radians per second? The 5, so capital omega is equal to, and that's a positive rotation about the z-axis, so that's 0, 0, 5. What about capital omega dot? Yep, that's 0. It's a constant angular velocity. And then the position vector. Of the point P, that's going to be 0.2 meters in the negative x direction, followed by 0.2 meters in the negative y direction. And now we have to calculate the observed velocity and observed acceleration. The observed velocity is equal to lowercase omega crossed with the r vector. What's lowercase omega? So now we're talking about, we're imagining that this thing is fixed. We're ignoring the motion of this, and we're just using this coordinate system to track the circular motion of P, okay? So omega is, lowercase omega is positive 10, 0, 0. That's rotating about the x-axis of the coordinate system. And the r vector goes from the center of the circular motion to P, not from the origin to P. So this is just going to be 0, negative 0.20. And so the observed velocity is just -2, nope. -0, 0, -2. Any questions? That's right, because that has to do with the distinction between R and P. Right now, what we're doing is we're doing circular motion in a coordinate system that we're imagining is fixed. And so the equation for that is omega times R, omega cross R. And now the observed acceleration of P, that's alpha cross R plus omega cross quantity, omega cross R. This one goes away because there's no angular acceleration of the body. And so you just have 10, 0, 0, crossed with the quantity 10, 0, 0 cross R, which comes out to be 0, 0, -2. And so you get 0, 20, 0. And now we can just fill everything in. The acceleration of P is equal to the observed acceleration of P plus omega dot crossed with the position, and that goes away because there's no omega dot. Plus 2 times capital omega 0.005 crossed with the observed velocity vector 0, 0, -2. And that one goes away because 0.005 and 0, 0, -2 are parallel. Plus 0.005 crossed with the quantity 0.005 crossed with the position vector, and the position vector is -0.20. And so what do you get for the final answer for the position? Five, 25, 0. Okay, so next time we're going to put the origin at the other joint. And recalculate. And we need to get the same thing. Okay, any questions about that? That's all.